Welcome to this explainer. Okay, we're jumping right in today with a brutal, high-stakes exam mistake that literally costs students their grade boundaries every single year. You know, when you're sitting in that exam hall, the difference between top marks and a complete zero often comes down to just a few extremely precise words. Let's look at a classic trap. So let's dive into this painfully flawed student answer. A network is when computers share Wi-Fi. Now, to a beginner, that probably seems kinda logical, right? But it scored absolutely 0 marks. Why? Because it completely lacks the precise framework the Cambridge examiners are looking for. It's way too informal, it relies on trade names like Wi-Fi, and it just totally misses the underlying architecture of what a network actually is. To dodge that examiner's red pen, we've got to upgrade our thinking. We need to use this exact 4-step formula to craft top-band responses. Whenever you're asked to define a system, you need to state the concept, provide evidence or data, apply scientific reasoning, and, this is the big one, use the exact examiner wording. So let's apply this directly to computer networks. The absolutely crucial point here is starting with the perfectly safe Mark Scheme-approved definition. A computer network is a set of devices connected through links. That's it. It's concise, it's highly accurate, and it perfectly sets up the technical vocabulary the examiner is practically begging for. Let's break that definition down into 2 main buckets. On one side, we have the nodes. This is your actual hardware, so a computer, a printer, or honestly any device capable of sending or receiving data. Then, on the other side, we have the links. These are the vital communication channels connecting those nodes together. You really want to memorize these 2 categories, because nodes and links are the magic words that unlock your marks. Now hold tight, because in just a minute, I'm going to reveal a hidden examiner clue regarding network layers that completely changes the game. It's a kind of insider secret that separates top-tier answers from the rest. But first, you need the architectural framework that actually makes that clue make sense. Section 1. Classifying network scales, from PAN to WAN. Let's see how we classify these networks depending on their scale, scope, and purpose. Notice how the usage and trust levels differ dramatically based on scale. A LAN, a local area network, is designed for an organization's internal systems, right? In one specific physical location. Then you have a WAN, a wide area network spanning huge geographical areas. But let's zoom in on the PAN, the personal area network. A prime example here is Bluetooth. It operates on an open wireless protocol for just a tiny 10 to 100 meters. And to put that into perspective, the speed caps out at around 1 megabit per second. Knowing these distinctions is absolutely key because they dictate the hardware and protocols used. Section 2, direct connections versus virtual tunnels, point-to-point and VPNs. Let's start with point-to-point networks. Think of this like a private VIP highway. It establishes a direct link between a single sender and a single receiver. Because there are no intermediate devices sharing the path, it is incredibly reliable. I mean, there are absolutely 0 intermediate failure points. Plus, it offers dedicated bandwidth and supports full duplex communication. That just means data flows both ways simultaneously, without any complex routing. Simple, private, and super efficient. On the flip side, we have the virtual private network, or VPN. So instead of relying on a dedicated physical wire between 2 points, a VPN allows data link layer protocols to be tunneled through a larger, often public network, like the internet. It uses open connections, or virtual circuits, to basically simulate a direct link. Now, while they're almost always used for secure communications across the public internet, here is a fascinating, highly tested fact. Technically, a VPN does not need explicit security features. Crazy, right? By definition, it doesn't strictly require authentication or content encryption to be classified as a VPN. Its defining feature is the tunneling and virtual circuits, not the encryption. This is a massive trap in multiple choice questions, so watch out for it. Okay, closing our open loop from earlier, here is that ultimate examiner clue. It's all about distinguishing specific OSI layers. Notice the exact boundaries here. The data link layer oversees delivery of a packet between 2 systems on the exact same network, or the same link. But the network layer, fundamentally different. It handles source-to-destination delivery across multiple networks. If you accidentally write network when you mean link, boom, the red pen comes out for sure. Furthermore, you absolutely must understand the transport layer. Error control here is performed end-to-end. The sending transport layer literally guarantees that the entire message arrives at the receiving end without damage, loss, or duplication. And how does it achieve this? Usually through retransmission. Getting the responsibilities of these layers straight is just vital for those high-mark answers. All right, let's play a quick game. Pause and predict. Based on the framework we just built, what is fundamentally wrong with this exam statement? A VPN uses a direct, physical point-to-point connection to secure data. Think about it for a second. Did you catch it? The examiner's red pen would strike heavily here. A VPN relies on virtual circuits tunneled through larger networks. That is the complete, literal opposite of a dedicated direct physical link found in a point-to-point connection. Mixing up virtual tunneling with physical wires shows a major misunderstanding of the architecture. Section 3. The Examiner Upgrade. From Zero to Top Band. Let's rescue that disastrous zero-mark answer from the very beginning of this explainer and build it into a flawless response. Watch this transformation. By taking vague concepts like computers sharing Wi-Fi and replacing them with precise scientific terminology, nodes, and communication channels, or links, you instantly lock in those critical marks. You've gone from a conversational guess to a scientifically reasoned fact. Let's do a really quick rapid-fire review of the core concepts you need to memorize. First, precise definitions of nodes and links. Second, scale classifications, especially the constraints of a PAN like Bluetooth. Third, understanding point-to-point's direct physical connection versus a VPN's virtual tunneled circuits. And finally, the distinct roles of the transport, network, and data link layers. Get those locked in your brain. Before we wrap up, make sure you subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to truly excel in your Cambridge examinations. We've got an amazing community over there, and honestly, mastering these network concepts is just step one of the battle. Which leaves us with a pretty critical, provocative question for our next explainer. You now have the precise vocabulary. You have the structural framework to get top marks. But can you actually apply this framework accurately under relentless 60-second per mark exam timing pressure? Because having the knowledge is one thing, but executing it flawlessly before the clock runs out, that's the ultimate test. Join me in the next explainer, where we tackle the timed answer writing system, and I'll show you exactly how to beat the clock. Catch you then.